Doing section 32, which is an introduction to related rates. So related rates is a very important AP Calc topic. Are you guys all paying attention? Computers are away, phones are away. So you're often going to see related rates problems on the AP exam. They're not only in the multiple choice, but they're also usually like one of the free response questions involves related rates. Okay, so super, super important. So we'll be doing a couple sections just involving related rates. So you're going to be given the rate that something is changing. Maybe it says that the height of the water is decreasing at -2 inches per second. And then you're asked to find like the rate of change of maybe the volume of the water, okay? So that's why it's called related rates. You're finding the rate that something's decreasing and relating it to the rate that another thing's decreasing or increasing, okay? In order to do these, we're going to differentiate both sides of the equation implicitly with respect to a new variable, time, okay? So look at the first equation. Notice how I have x and y. I'm not going to take the derivative and just say that it's 4x cubed plus 3. Can't do that, okay? I'm going to take the derivative with respect to time, with respect to t, okay? So, when I take the derivative of y, the derivative of y is 1, and it's dy over dt, not dy over dx, okay? So it's going to be dy over dt. And the derivative of x to the fourth is going to be 4x cubed dx over dt. So every single thing is going to get something with a dt. Okay, and then the derivative of 3x is 3 dx over dt. Okay, and then it says certain things. So it says that x changes with respect to time at a rate of 5. Okay, so we replace all the dx's over dt's by 5 with 5. And then we replace the x with what? With 2. So we're going to say 2 cubed. And then we're able to solve for dy over dt. So dy over dt is going to equal 4 times 2 times 5 is 160 plus, isn't it 160? 4 times 5 is 20 times 8 is, yeah, it's 160. And then plus 15.
It wouldn't be 4 times 2 times 5. Yeah.
It's 4 times 5, which is 20, times 8. 20 times 8 is 160. I think I'm right. All right, so I get 175, and that would be the rate of change of y with respect to time. Okay, so this one is kind of a nonsensical equation. It doesn't make any sense right now. There's no like actual equations that we know, like volume, area of a rectangle, things like that. Okay, we're going to actually do like the real life type questions. Okay, and when we do these real life questions, we're going to draw a sketch. We're going to set up an equation relating all of the variables. We're going to differentiate implicitly with respect to time, substitute in everything we know, always after we take the derivative. Because what happens if I plug in all the numbers I know and then I take the derivative?
It's not going to work because you'll end up having a bunch of zeros.
Yeah, like you'll get a bunch of zeros, right? And then we're going to solve for the remaining rate that we need to find. Okay, so let's do an example. We'll do some examples that make more sense. All right, so it says a 10-foot ladder leans against the side of a building. So we have our building, and we have our ladder. If the top of the ladder begins to slide down the wall at a rate of 2 feet per second, how fast is the bottom of the ladder sliding away? You would think that these are the same. They're not actually the same. I should show you videos of these ladders falling. Okay, so we're going to set up some variables, and the one that makes sense a lot of times with vertical and horizontal directions are x and y. So I'm going to do x, y, and I'm going to call this z. Sorry, told you, I'm dying up here. All right, so, I know, hopefully not. All right, so I'm going to go ahead and set up an equation that relates these variables. So what's an equation that relates x, y, and z?
X squared plus y squared.
Pythagorean theorem. X squared plus y squared equals z squared. What? All right, so, and then we're going to take the derivative. So when we take the derivative with respect to time, we're going to have 2x dx over dt
we know that z is y,
plus 2y dy over dt equals 2z dz over dt. So we don't plug in any known values because when we take the derivative of everything, if we knew all the values, then all those derivatives would be 0, right? So we're going to leave it like that. Now, Julia did say, well, we do know that the ladder is 10. We do. That is the one and only constant that you can plug in.
So Z is 10.
Z is 10. So I'm saying, like, before we took the derivative, we could have plugged in 10. So I want you guys to think about that as we do this. Yeah. Okay, so y is equal to 8, so we can plug in now. We can plug that in now after we've taken the derivative. But if I plugged it in before, like y equals 8, when I take the derivative of y squared, 8 squared,
64.
its derivative would be 0, right? So we don't want to do that. So there are instances when we can plug in values, but I want you to think about when those instances are, okay? All right, now a lot of times when I have the Pythagorean theorem, I just kind of get rid of these 2's because I can divide by 2 on both sides. Less things to plug in for. Less writing. All right, and let's write what we know. So it says that we had a 10-foot ladder. So that's going to be our Z. And it says the top of the ladder begins to slide down the wall at a rate of 2 feet per second. So this y, dy over dt, is kind of 2, but not really 2. Do you guys see how this distance, are we gaining a distance or losing a distance?
So it's negative 2.
It's getting smaller by 2 feet every second, right? So after a single second, it would no longer be at the height it's at. It'd be 2 feet smaller, right? So it's going to be negative 2. And then how fast is the bottom? dx over dt is what we need to find. What about dz over dt? Why do you say that? You're correct.
What did he say?
He said 0. So Emerson says 0.
Because
It's a solid. I know what you're saying. So it is a constant, would be the word. It's a constant length. I think it would be a really cool calculus problem if I did this to you. If the ladder was falling down the wall and it was like detracting, like getting smaller. Have you seen those ladders like get bigger and smaller? That would be a really cool calculus problem. I'm not going to do that to you though. So this ladder is like a fixed 10 feet tall and it is falling. So is it changing in length? No, if it's not changing in length, then our dz over dt is constant. It's like dz over dt, it doesn't change at all, so it's 0. Right? It's not getting bigger, it's not gaining 2 feet per second or losing 2 feet per second or anything like that. Does it make sense? So this right here is 0. So this is 0 because ladder is a fixed length. So we call that a constant.
Wait, so does that make the other side of the equation equal to 0 because z times dz?
Well, we got to solve for something, right? All right, so what do we know? So we know we have 10. We said how fast is the bottom of the ladder sliding away when the top is 8 feet off the ground? So y is going to be 8. So if I have a little triangle and I have 10 and 8, that's a right triangle, then what's the missing one? 6. Do you guys all know that? 3, 4, 5. I didn't draw it very well, but you guys see that? I don't speak Spanish. I took French, which, you know, it was all right that I took French, but I wish I knew some Spanish. I do know C. I can handle that. All right, so x is 6. And then dx over dt is what we're trying to find. And then y was 8, and dy over dt was negative 2. So now we can solve. So we have 6 dx over dt minus 16 equals 0. So we get 16 over 6 for dx over dt, which reduces to 8/3. Or if you wanted to write it as a decimal, 8 over 3. I don't know why I'm putting this in my calculator. It's 2.6 repeating. I know, where's my Ian when I need him? All right.
You want me to say
All right. So what do you think my units are? So the units have to do with the variables. Look at it. So what was x in? X was in terms of feet. What was t in terms of? Time. So when you have dx over dt, change in x over change in time, it's going to be in feet per second. So our units are feet per second. And that's our answer. All right. So the next step. So it says, suppose a forest fire spreads in a circle with radius changing at 5 feet per minute. Okay, and it kind of makes sense if you think about it. If you start out with a forest fire and you are at your little campsite and it's just like a tiny little radius that's only 1 feet wide, can you put out that forest fire pretty quickly?
Yeah.
1 foot wide.
If it's only 1 feet in width, I think you can probably put out that forest fire, air quotes, pretty quickly, right?
That's probably
If it's a radius of 200 feet, can you put that out pretty quickly?
No.
No, it's probably spreading pretty darn fast. Do we agree?
You're probably dead too.
So the rate of change of the area is pretty quick. By the bigger and bigger the radius gets, right? Okay, so it says when the radius reaches 200 feet, at what rate is the area? So we want the area of this circle. How do I write the area of a circle?
Pi radius squared.
Yeah, area is equal to pi r squared. So let's think about what we're trying to find. We said the radius is changing at a rate of 5 feet per minute. That's our dr over dt. So sometimes it helps to kind of write down what we know. So we know dr over dt is 5 feet per minute. And what do we want to find? We want to find dA over dt at a certain point in time, right? So when r is equal to 200. So at that certain time.
So do we derive the area function?
Look, we take the derivative, so I do dA over dt equals, and you can kind of separate, you can leave the pi out front and take the derivative of r squared as 2r dr over dt. Or you can do it all together and write 2 pi r dr over dt. That's fine. So we're going to have pi times 2 times, at that point in time, our radius is 200. Our dr over dt is 5. So putting it all together, we get 2,000 pi.
So that's an answer. That's 1,000 pi feet per minute.
Yep. Well, is it feet per minute? What do we think?
Feet squared per minute?
Yeah, feet squared per minute. Do you guys see why it's feet squared? Right, because it's the rate of change of the area with respect to time. Right, area is feet squared. Square feet. Okay, so that's our answer. Now you could find an approximation in decimals. It'd be 6,283.185 if you want to do that as well.
That's a very fast burning fire.
It is very fast. Only you can prevent forest fires.
Unless they're at this point, then just run.
Yeah, that's true. All right, so here we go. So didn't we talk the other day about the oil spill? I don't remember why we were talking about it, but all right. So an oil tanker has an accident on a bridge, and oil spills out at a rate of 20 cubic feet per minute. So when you see things like this, you should recognize what you have. When you see 20 cubic feet per minute, what's that the rate of change of? Not an area. Volume. Do you guys see? Cubic feet. So it's going to be dV over dt. That's okay. And it's spilling out. So am I gaining volume?
No.
Losing volume? So it's negative 20. So that's one thing we know. Okay, and it's spilling out. Usually oil will do this for a certain amount of time, and then all of a sudden it starts kind of dropping into the water. But have you ever spilled I don't know, vegetable oil on water, and you kind of watch as it spreads out along the top? It doesn't really mix
I
in
had
well.
an oil fire and I put water in it.
Oh, don't do that.
It burned the kitchen.
Yeah. Oh gosh, dangerous.
Oh,
All right, so we have the circle, but it has a thickness. And so we're going to assume that this is like a uniform thickness for a while, and then I'm sure after a certain amount of time it's going to start sinking in. But it says, suppose that the oil spreads out onto the water in a circle with a thickness of 1 over 10, so 1/10 of an inch, or 1 over 1/20th of a foot. Now, in this case, I think we want to use the feet. Do you guys think we want to use the feet? Yeah, because our volume is in terms of cubic feet, right? So I would use feet. That's the only good my almost art major has for me right there, drawing cylinders. It's not even that good of one. The side is struggling. All right. So determine the rate at which the radius of the spill is increasing when the radius equals 500 feet. So we're trying to find, so we want to find dr over dt when r is equal to 500. So r isn't always equal to 500, right? R is changing. So we're going to find out when it's equal to 500. So we have the volume. The volume of a circle That doesn't work. It's not a circle, right? What is it?
A cylinder.
It's a cylinder. So it's pi. Do you guys remember the volume formula for a cylinder? You need to know all of these.
4/3.
Nope, that's for a sphere.
That's for a sphere.
It's the big ones that you guys need to know are either volume equals area of the base times the height, or the volume equals 1/3 the area of the base times the height.
Do that.
1/3 is for anything that goes to a point, like a cone or a pyramid.
Like how 1/2 is for a triangle.
And then these are for cylinders and prisms. Okay? So what do we have? We have the cylinder, right? So it's going to be area of the base. So the area of the base is a circle. So pi r squared h. So you can carry on from here and you can take the derivative, but it's going to involve the product rule. Do we all see product rule? Pi r squared times h. The area of a circle is pi r squared.
Right, but there are two.
No, because you just use one of the bases. We'll talk about where that comes from. That's geometry. I don't know. What's the formula? I mean, it has to do with calculus. So we'll talk about calculus later. All right. So you can do this from here, but remember that example that we had with the ladder? And I told you occasionally you can plug a number in, and I told you you could plug a 10 in. Why would I have been able to plug in this length here, 10, into the original formula? But nothing else. I couldn't plug in the 8 or the 6.
Because it was being multiplied by something else that would not change when you derive it.
Yeah, like when you took the derivative of it, like you would have a dz over dt. Is that what you mean? And the dz over dt was 0. Do you see that?
Yeah.
So what's our little like rule here? We can plug numbers in only when they are constants. Okay, that's something that will be very, very handy to you. And I've gone to many an AP conference, and I've listened to teachers say, "Oh, I never let my students plug in constants. I just never do because when they plug them in, you know, they just make mistakes all the time, and they try to plug it in when they can't plug it in." I'm like, I just teach them that they can only plug in constants. Do we all understand you can only plug in constants? If something's changing, you don't plug it
What do
in.
you mean constant?
So something that's a constant number, like this 1/120. It's a constant thickness. It's not getting taller or smaller, right? So we can plug it in. All right, like that ladder. That ladder wasn't like getting bigger or smaller, right? So we can plug it in originally. So we're going to go ahead and plug in h is 1/120. Because there's one that we do later that's called a trapezoidal trough problem, which is like this. Chuck Webster walked in while I was teaching this last year, and I was just like, he is so confused right now. But it involves L, it involves B1, B2, the height of the water, so H. There's a lot of variables going on in a trapezoidal trough. So you want to plug numbers in if they're constant, right? Yeah, it is. It's a joy. All right, I like it. All right, so pi times 1/120 is going to be pi over 120, and then r squared. Now we take the derivative. So dv over dt is equal to, you can keep that pi over 120 out front if you want, and just take the derivative of r squared is 2r dr over dt. Okay, so when we plug things in, we know the rate of change of the oil is we're losing 20. Actually, we're not losing. It's not like leaving anything, is it? This is positive 20. Sorry, I don't know why I did that. We have ones where it's like a funnel and you're like the volume is leaving like a funnel. That would be where you're losing a volume. So we're going to have 20 is equal to pi over 120 times 2 times r is 500. And then dr over dt is what we're trying to find. Okay, and we're going to solve it out. So I'm going to do the 20, I'm going to multiply by 120, I'm going to divide by 1,000. So I'm going to get 12 over 5 equals, and I have pi times dr over dt. So when you get to this point, a lot of people make the mistake of like putting the pi on the top, like they put it up here. We're dividing by it, right? So it's going down here on the bottom. Everybody find that decimal approximation for me. All right, wait. Don't blurt it out. Because this is a mistake that a lot of people make. Alex?
I'm pulling my calculator.
Uh-huh.
I'm gonna be faster than he is.
Yeah, you should get point. He's already said it a long time ago. 0.764. And your units are feet
7.53.
per, what is it, second?
My calculator lied.
That's what I was telling you. A lot of people will mess that up.
Oh.
So it's feet per minute.
Yeah.
Okay, so the thing that you guys did is if you do 12 divided by 5 pi on your calculator and it doesn't have the fancy font that puts it like 12 over 5 pi, when you put this in, it does 12 over 5. It takes that result and multiplies by pi. So you have to put parentheses around that bottom.
Yeah, it's very important.
It is. It is.
Oh, you should get
Crucial.
7.53.
Oh yeah, that's not.
You're still doing the same thing. So 12 divided by parentheses 5 pi parentheses.
Oh, Louis, you
0.764.
did it. I'm proud of you, Louis.
All right, but you can also leave it as the 12 over 5 pi. I'm cool with that. And then be careful, like a lot of times it's nice to write kind of a final sentence. So determine the rate at which the radius is increasing. So the radius is increasing at a rate of 0.764 feet per minute. But if it had been decreasing, let's say it was negative, and it says determine the rate at which the radius is decreasing, would you write negative blah, blah, blah?
No.
No, it's a double negative in the math class. You cannot do that. So you would say the rate is decreasing at the positive number. Or you would say the rate is changing and then put the negative. Does that make sense? So be careful. All right, so a snowball. What shape is a snowball?
Spear.
No, it's a sphere. And what's the surface area of a sphere?
Good question.
I think we just talked about this the other day. The volume of a sphere is 4/3 pi r cubed. The surface area is its derivative, 4 pi r squared. So we're not using the volume equation, but.
Are we supposed to know these?
Yes. This is why you take classes like geometry. You should know these.
I was like,
Yeah, I don't think we actually.
Really?
I don't remember where.
Here?
4/3 pi r squared cubed.
4 pi, or 4/3 pi r cubed is the first one, and then the volume, and the surface area is its derivative, 4 pi r squared. Okie dokie. So it says find the rate at which the diameter decreases when the diameter is 10 centimeters. Okay, so you could notice, oh wait, it's talking about diameter,
But that's just 2R.
but we have everything in terms of radius. So there's a couple different ways you can do this. Let's say, like in the first class, what I did is I was like, I just powered through and I was like, oh wait, I forgot that it said radius. Or diameter. I had already taken the derivative, 4 pi 2r dr over dt, and I'd found my dr over dt. So ds, it's decreasing at a rate. So it's a -1 there. And I have 4 pi, and then, yeah, go ahead and write it in. And then if diameter is 10, what's the radius? 5. So we solve for dr over dt. We get dr over dt equals -1 over, let's see, 40 pi. Right? And then we're like, oh no. Oh no. dr over dt, not dd over dt. And this will happen to you. You guys will have questions on your homework and your tests and so on when you like just start powering through the problem and you're like, oh, I'm getting it. And then you're like, oh crap, I didn't find what I was supposed to find. That is totally fine. There's a way to fix it. This is why we call it related rates. Everything is related to other things. Okay, so our diameter and radius related to each other.
Yes.
What equation relates diameter and radius?
2R.
So we write it. So we say, okay, well, I know that d is equal to 2r. So their derivatives are also related. So their derivatives, if I take the derivative of this equation, dd over dt is equal to 2 dr over dt. Isn't that nice? You can always fix whatever problem you run into.
So dt over dt is equal to -1 over 25.
Yeah, so we multiply in, so I have -1 over 40 pi. So I get -1 over 20 pi. And you can find the approximation if you want to. Ian's already on it. What is it, Ian?
-0.016.
And our units would be,
Centimeters per minute.
yeah, centimeters per minute. So you can do that if you want to. Okay? So let me show you really quickly. You don't have to write this because you already wrote all that down. But kind of look up here, and I'll show you the other way. I'll do it really quickly. So our other way is if we notice that we were good students at the beginning. We're like, oh, wait, it asks for the rate of change of the diameter. Then we replace our r with d over 2, and we square it. We always simplify before taking the derivative because we don't want to take the derivative of this in the more complicated form, right? So I get 4 pi d squared over 4, which gives me the surface area is equal to pi d squared. That is another equation for the surface area of a sphere, pi d squared. Pretty easy, right? So when I take the derivative, I end up getting 2 pi d dt over dt. I love when there's lots of d's. And then we plug everything in. So the diameter is 10. This was negative 1, right? So I get negative 1 equals 2 pi times 10 dd over dt. So we end up getting exactly the same thing, right? So you can do it either way. It does not matter. That's why we call it related rates. All right, next up. All right, this one's kind of a weird one, and it helps if you kind of like think about how to sketch this in the best way possible. So at noon, ship A is 100 kilometers west of ship B. So at 12 o'clock. So ship A is sailing south at 35 kilometers per hour.
Oh, it's a bearing problem.
Kind of. And ship B is sailing north at 25 kilometers per hour. Okay, it says, how fast is the distance between the ships changing 4 hours later, so at 4 o'clock. So here's the distance between the ships. I'm going to draw it in red. And you can do like 2 crazy right triangles, but it gets to be a lot. There's a lot going on there if you do that. So the easiest way to draw this sketch when you see this happening is to realize that this total distance right here and this total distance right here. So what is the vertical line? How much is this changing by? Not
60,
35,
60.
yeah, but 60 kilometers per hour. Do you guys see that? Because one is going up and one is going down. One's going at 35 and one's going at 25, so total it's 60. Do you guys see that? How about the x direction?
It's not changing based on
It's not. Yeah, so that's our x. So dx over dt is equal to 0. Sorry, that's super tiny.
Why wouldn't there be like a horizontal distance between
Because it started out 100 kilometers apart, so this was 100,
them?
and so it's still that 100. So that's a
So
constant.
that's
Yeah, so you can just leave it in there. And then this y and z. Okay. So when we set up our equation, we have like 100 squared plus y squared plus here equals z squared. So you could have left it as x squared, and then dx over dt is 0 anyway. So we take the derivative, so we get 0 plus 2y, 2y dy over dt equals 2z dz over dt. Start plugging things in. So it says, how fast is the distance between the ships changing at 4 p.m.? So at 4 p.m., can you guys tell me what this vertical distance is right here?
240.
240. Does everybody else see why it's 240?
No.
Because
60
every
per hour.
single hour you increase by 60 kilometers.
Oh, so you do that times 4?
Mm-hmm. So it's 240. And then we have 100, and then this z we can get by doing the Pythagorean theorem. It ends up being 260. So it was from 240 squared plus 100 squared equals z squared. It's a 5, 12, 13. Math teachers like 3, 4, 5 right triangles and 5, 12, 13 right triangles. So we plug in. So we have 2. We have 240. We could also cancel the 2's originally. Dy over dt is 60. And then dz over dt is what we're trying to find. And z is 260.
Wait, where did you get that y over dt is 60?
Because one was going south at 35 kilometers per hour and one was going north at 25. So together it's increasing by 60. Does that make sense? It's kind of weird. All right, so when I divide all of this out, I'll just use the decimal. We get dz over dt, that's a weird dt, equals 55.385 kilometers per hour. Which makes sense, right? If you get something that's like 1,010,000 kilometers per hour, it's probably not 1,010,000 kilometers per hour. You probably did something wrong, right? Okay, and the last one we have to talk about is one that happens a lot in real life. So I think I did one like this last year in pre-calc, not a related rates problem, but I talked about like grain silos. Do you guys remember that?
Oh, I
Yeah.
remember that. Oh, yeah.
So like anything that has like a cone on the bottom, like silos are like that, where you're like driving a truck up underneath it and then you're dropping a bunch of stuff into it. Like we use cones a lot in real life, any funnel that we have. So an inverted conical tank. So this is a cone, but the tip of the cone is at the bottom. It's leaking at a rate of 6 cubic inches per minute. So it's leaking out, and we're losing, so dV over dt, we're losing 6 cubic inches every single minute. So it's a negative. I always draw this cone totally wrong. Mine's never like drawn to scale. I'm gonna fix mine. You don't have to fix yours, but
Looks like a snow cone.
it's kind of a fat cone. Okay, so it says the height is 12 and the radius is 15. It's still not really drawn, but that's okay. Better than it was.
That's a really small tank.
All right, every single time that you guys have these, you are going to use similar right triangles. Another geometry concept that you may have forgotten long ago.
Long ago, 4 years ago.
Yeah, so I don't know, do you guys remember this? If you have 15 and you have 12, still didn't draw to scale, and you have R and you have H, do you know how to set up a proportion with those?
Yes.
15 over R equals 12 over H, right? So like the big radius over the radius of the water equals the big height over the height of the water. Yeah?
Yeah.
All right, we're always going to use that.
Oh, we gotta go.
Lucky you. All right. I'm going to finish it. I don't care. All right. So the big thing with these is, if possible, I mean, you can do this with the product rule. You can do it, and it will be fine. And that's what a lot of calc teachers like will have you do. I'm not going to have you do that. On these cone problems, you can always get one of those variables by itself. So if I like want to solve for, I don't know, what does it say? Find the rate of change of the radius. So if I want to solve for H is equal to 12 over 15R, which is 4 over 5R. It is always easier to only have one variable. So see how H, I can make it into 4 over 5R, and I can simplify this stuff. So I'm going to simplify it. So I get 4 over 15, and then times pi. So I'm going to do 4 pi over 15, and then R cubed. So I'm just simplifying it. Yeah, Emerson?
So it gives you the height of the water.
Yeah, it doesn't matter which one it gives you. And I kind of did a combination. It says find the rate of change of the radius when the height is 8. Well, you can always find the radius when the height is 8 using this. So still using this. Okay. So it doesn't matter which one you solve for. All right, and then we take the derivative. So dB over dt is going to be 4 pi over 15. And then I'm going to have my 3r squared dr over dt. And then what Emerson is saying is they gave us the height of the water was 8. So if I know that h is equal to 4/5 r, and I know my height is 8, I can solve for r. So multiply the 5 over and get 40, divide by 4. So r is equal to 10 at that point. So then we plug in 10. And then we have everything else. So we want to find the rate of change of the radius. Ian, are you finding it for me? And then the dB over dt was -6. So I'll find it as a decimal.
You should get -0.23.
I had negative 0.0 yeah, 239 is what we're saying?
Yeah.
So 0.024, we'll say that. And then inches per minute. I think that's what it is. Sorry, YouTube viewers, if that's wrong. You guys can check that, right? All right.